Can you hold this again, Steven?
Yes.
Alright, so we know that the volume of a spherical balloon is... Oh, that's just a terrible pen. Volume is equal to 4 over 3 pi r cubed. And so the first step is to implicitly differentiate this volume equation. So that would equal to dv over dt is equal to 4 pi r
Kevin,
squared.
why do you use the dt?
dr over dt. Well, it's because we are differentiating this equation with respect to time. So all we have to do is plug in what we know. And we know that I'm blowing into the balloon very hard, as much as I can, at a constant rate of 5 centimeter cubed per minute. Let me write that down, 5 centimeters. So I'm blowing air into the balloon at a rate of 5 centimeters cubed per minute. So now all we have to do is plug in what we know. So dv over dt is 5 centimeters, no, sorry, wrong side again. 5 centimeters cubed per minute. So the diameter is 20. That means that the radius is 10 squared dr over dt. And so now we can solve for what we want to find. So we want to find dr over dt. So then dr over dt equals to 1 over 80 pi centimeters per minute. And that is the rate at which the radius of the balloon is increasing when the diameter is 20 centimeters.
Wow.
You understand?
Yes, I do, Kevin. You're so intelligent.
Thank you. You have fun with those balloons now, Steven.
I will.
You have fun at that party.
Yes. Finally got my balloons. Yes.
Oh no!
No!
Steven, it's okay. This is a good learning experience. Let me apply some calculus to this problem.
How, Kevin?
Two objects, me and the balloon,
Yes.
are 15 feet apart. And the balloon starts floating north at a rate so that the angle is changing at a rate of 0.01 radians per minute. So the problem is, at what rate is the distance between me and the balloon changing when the angle is 1.5 radians?
I get that, Kevin. So to solve this, I'm assuming you use right triangles.
Yes, and the power of calculus. It's heavy, it's pretty heavy. So, okay.
Wow.
The formula that we're going to use to relate the rates is secant theta equals x over 15, because secant is equal to the hypotenuse over adjacent, and according to this diagram, it is x over 15. So we have to differentiate this equation, which will turn into secant theta tangent theta d theta over dt equals to dx over dt all over 15. Then we're going to multiply 15 onto the other side and plug in what we know. So we know that 15's here. Secant times 1.5, which is the angle that we're trying to find, times tangent 1.5 times 0.01, which is the rate at which the angle is changing, equals to dx over dt. And when we solve that, dx over dt equals to 0.0039 feet per second. So that means that the distance between me and the balloon is changing at a rate of 0.0039 feet per second. Isn't that interesting?
Wow.
Wow.
That is,
Wow.
I'm not even sad about my balloon anymore.
I know.
I'm astonished.
Good job.
What a day.
It's been an interesting day, huh, Steven? Yes, it has, Kevin. We learned about the fish tank, the balloon problem, and now the angle problem. I hope you learned a lot about calculus today.
I did know. Like, I did not know that you can use calculus every day.
You can use calculus every day of your life.
Bye, Kevin.
Until tomorrow, we will learn about calculus again. Goodbye. Wait, I just thought of another problem.
Yes!
And in this crazy life, and through these crazy times, it's you, you make me sing your every line, your every word, your everything.